time for us to do some problems involving alternating series test, which also means we'll get to look at things like absolute convergence versus conditional convergence versus divergence. Now, the alternating series test is oftentimes people's favorite test because it's so simple. Do you alternate? Do you go down to zero? You're looking great. All right. So, of course, there can be some subtleties, and we'll see some interesting things as we go along. So, of course, as always, practice is important. The more you practice, the more comfortable you get at doing problems. So do as many as you can. If you're following along, make use of the pause button. You see a problem, try it yourself first. See how far you can get. And if you're ever stuck, that's all right. It's just a pause button. You can unpause me, and then we can figure it out together. Well, let's begin. Our first problem. Determine if the following converge or diverge. And this is not meant to be anything hard or tricky. It's just we're going to answer the question, boom, 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 boom. So the sum 1 to infinity, 1 over n squared. Converge or diverge? Well, it's a p-series. And here we see it's a p-series. P equals 2. That's bigger than 1. So this will converge. And indeed, we can actually say why. It's p-series. Now, here, negative 1 to the n over n squared. Does this converge or diverge? Well, this will also converge because it's alternating. That's the minus 1 to the n. And we have that n squared downstairs, which drives things to 0. So it's alternating and going to 0. So this is by alternating series test. Now notice we can't do a p-series test here because of the alternating sign. A p-series, you need to assume it's all positive. But if we drop the alternating sign, of course, we would see, aha, it does converge. All right, well, great. So what do we see? Next pair, 1 over n. All right, that one we know. We've talked about this one explicitly. This is the harmonic sum, and so we know that will diverge. But add that minus 1 to the n over n. Well, hey, now you're alternating. That's great. Now we just say, does 1 over n go to 0? And it does. So this will converge. And this is alternating series test. All right. Well, how about the sum of just n? 1 plus 2 plus 3. No. Diverges. Why? Well, because the terms don't go to 0. So this is the nth term test, or our basic divergence test. Oh, wait, what if we alternate? Minus 1, plus 2, minus 3. Forget it, same problem. Terms aren't going to 0. So this will also diverge. Okay, nth term test. Now, what's the moral here? You can see that there can be different things happening. See, sometimes it converges if we don't have the sign coming in. And if you add the alternating sign, it can still converge. Sometimes it will diverge without the alternating sign, but then if you add it, it does converge. And sometimes things are just outright diverging. So this is somehow the difference between the sort of philosophies absolute versus conditional versus, all right, forget it. See, absolute says, hey, it doesn't matter. I don't need that plus minus. Conditional says, ooh, I definitely need it. Without it, forget it. And here, it just says, hopeless, forget it. Now, you might say, well, hey, I see there's 3 things happen. Converge, diverge, and diverge. Is it possible that I can get a sum of positive things which would converge, but when I add that alternating, it diverges? And the answer is no, it's not possible. So these are, in essence, sort of the 3 things that can happen when you take a sum of positive values and then say, well, what happens if we throw a plus minus alternating thing going in? All right, well, good warm-up, right? Now for the fun part. Okay, next question. Determine if the sum from 1 to infinity of minus 1 to the power n plus 1 times log of n plus 1 over n converges. Okay, well, what do we see? Now, we have done things like this before. If you took off the minus 1 part and you had that log of n plus 1 over n, we said, oh, that looks like telescoping, but oops, it's telescoping where the n drifts up and gets big. So we have in the past seen that without that minus 1 to the n, forget it, diverges, telescoping. But now we have that minus 1. So our question becomes, okay, what do we need? Well, we see this part is alternating. That's clear. And now the question is, does this go to 0? And if the answer is yes, then we're good to go. So let's think about it. So log n plus 1 over n, take the limit here as n goes to infinity. And we can say, all right, well, that's the same as limit as n goes to infinity, log of 1 plus 1 over n. And, well, that goes to, see, there's only one n left. And as n goes to infinity, 1 over n gets small. Goes to log of 1 plus 0, which is log of 1, which is 0. And so the terms go to 0. Now, technically speaking, yes, when we talk about our alternating series test, we have to have a case where the terms go to 0 in a nice fashion. In other words, they're monotonically decreasing. Any reasonable function that we encounter will be monotonic in the long run, as things like log 1 over n to a power, so forth and so on. If you have something like sine, it can get kind of interesting, sine and cosine. But most functions that we encounter will behave like we expect. So we go to 0, we alternate, so it does converge by the alternating series test. And now we're done. The answer is yes. Great. Well, that one doesn't seem so bad. Huh. I wonder why it's there. Well, turns out it's related to the next one. So, what can we say about the following infinite product? Well, that's an interesting question, isn't it? So, because we haven't talked about infinite products, we've talked about infinite sums. So, we now know it can happen that if you add up infinitely many numbers, you can end up with a finite number. So is it possible that you can multiply infinitely many numbers and end up with a finite number? Now, sometimes we can say, oh yeah, it's easy, like a half to the n, which is a half times a half times a half. Infinitely often, well, that's going to go to 0. Okay, but can you have something about where you have infinitely many numbers multiplying and you don't go to 0? Maybe you go to some other number? So, what do we do? Now, the first thing they might say is, how can we approach this? Because we haven't developed the theory. Well, what we can do is say, let's somehow connect back to what we have done. We're looking at an infinite product. We'd like to say, can we think about it as an infinite sum? So, the question, is there something that lets us turn a product into a sum? Some function or machinery that says, hey, if I have a bunch of things multiplying, it really is like a bunch of things being added. Well, we start reviewing through all of our different math logs over the years and say, there's something that seems to do that. What does that? What does that? Logarithms do that. You see, we have this fun fact. The natural log of two things multiplied together is the same thing as two things being added. So we can think about taking the natural log of this infinite thing. Of course, what we really mean is take the natural log of some finite part and then just keep expanding it. So let's think about what this is really saying. So if we take the natural log of this expression, what do we have? Well, it's the natural log of 2 over 1, and then it's plus the natural log of 2 over 3, plus the natural log of 4 over 3, plus the natural log of 4 over 5, plus, and so forth and so on. And hopefully we can convince ourselves, okay, that's what's going to happen. Certainly it's what happens to any finite part, and then we say, okay, now dot, 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 dot. And now we say, great, but how do we make progress here? Well, one of the things is, if you look, natural log of 2 is positive, but natural log of 2/3 is actually negative. In general, if you have a number above 1 and you take the natural log, you get a positive number. If you take a number below 1, you're going to get a negative value. And if you think about this, it actually kind of makes sense. See, what we have is something bigger than 1, something below 1, something bigger than 1, something below 1. So it's like, oh, we're multiplying by a big number that sort of says grow, then a smaller number says, no, come back, then grow a little bit, no, go back. And so we're just sort of doing this C sign action here. So let's actually do the following. Anything where there's a negative value, let's actually write it as subtracting something. So the way we can do it is you can flip the log. What is the effect? If you flip the inside, that's as if you're taking things to the -1 power. So that means put a minus in front. So this would be log 2 over 1 minus log 3 over 2 plus log 4 over 3 minus log 5 over 4 plus log 6 over 5 minus log 7 over 6. And now we're like, whoa, this is all of a sudden feeling a couple things. It feels more familiar, but it's easier to spot some patterns. We see we're alternating plus, minus, plus, minus, plus, minus. So we can say, all right, what's our pattern? It's the sum where, let's say we start at 1, go to infinity. We're going to start on a positive note. And since we're alternating, it's -1 to a power. Because we're starting at n equals 1, we should shift and start at +1, right? So that way at 1 you get a positive, at 2 you get a negative, and so forth and so on. And then we have a log of a ratio. Now notice the downstairs, 1, 2, 3, 4, 5, 6, 7. That's n. The upstairs, 2, 3, 4, 5, 6, 7, 8. That's n plus 1. Now, have we seen this sum anywhere before? Anywhere at all? Well, I claim if we go back to the previous problem, it looks a lot like that sum that we just talked about. I said, oh, it's this alternating, and then there's this log of n plus 1 over n. It's the exact same sum. And so, what do we have? Well, we know that this sum converges. Now, we don't know what it converges to, but we do know it converges to some finite number. All right, well, since the sum converges, see, the sum is saying what happens when you take the log of the product. So, our conclusion is the product converges. And there we go. So even though it's like, wow, when did we talk about infinite products? We have, oh yeah, we can have this tool which lets us hop back and forth between sums and products. And so we can even start talking about what's happening with these products of things. And now it's sort of all sorts of fun and interesting questions that we can ask. All right, well, good. That was a little different. So let's try another one. So, our next problem. Determine if the following are absolutely convergent, conditionally convergent, or divergent. So you have three sums. And I'll go ahead and tell you that there's one of each. So, in other words, there's an absolutely convergent one, a conditionally convergent one, and a divergent one. So, now that's not what the problem says, but that's an extra bonus for listening along. Thanks for watching. Your support's appreciated. Let's go through and talk about these various pieces. Now, some of these are pretty easy to spot, and other of them, well, they're a little bit more subtle to spot. So let's talk about the first one. Now, you notice that we started at 1,000. Again, don't worry where you start. It's not about where you start. It's about where you end up as you head off to infinity. So we see there's a minus 1 to the n. That means alternating, and log, log, log n. Now, log, log, log n, and it's kind of fun to say, a bunch of logs in a row, but what's true? It's going to grow very, very slowly, but it will grow. So the denominator is going to get bigger as you let time move forward. So we say, oh, well, this alternates. And on the other hand, this part here gets big, which means since the denominator gets big, the whole thing is going to go to 0. So if you alternate, you go to 0. What's true? Well, what's true is that we can say, okay, this will converge. And why will it converge? That's by the alternating series test. Now, what if you remove the alternating series? Okay, think about the following sum. N equals 1,000 to infinity of 1 over log, log, log n. Now remember, log, 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 log n. That's growing very, very, very slowly. And in particular, it's smaller than n. So, since this is smaller than n, just this denominator, this is bigger than the sum if we just put 1 over n downstairs. But this is going to be large. It's part of the harmonic series. So we say, you need the alternating part because the growth is very slow. Slow growth usually means diverging. But when you throw in the alternating, then that's usually enough. Of course, you have to make sure it goes to 0. So the first one is conditional. All right, so there we go. That's a conditional sum. Okay, well, great. 2 series left. How about the next one? Minus 100 to the n over n factorial. Now, we think about rates of growth, and we know that we can talk about exponential versus factorial. And factorial beats exponential. So in other words, the denominator is growing much, much faster than the numerator. So we say, since the denominator is growing a lot faster than the numerator, it should be going to 0 pretty quick, which means we think it should converge. So we think that this is going to converge without the minus sign. That's our gut feeling moving into that part. Okay, well, if that's the case, we say, great. Well, what can we do? Well, let's compare without the minus sign. So 1 to infinity of 100 to the n over n factorial. And here, if we were thinking about a convergence test, the right test to use is ratio, because we see a factorial. So here's our a sub n. We'll look at the limit as n goes to infinity of a n plus 1 over a n. So that's our limit. N goes to infinity. So 100 to the n plus 1 over n plus 1 factorial. That's our an plus 1. An, flip in what the term is, n factorial over 100 to the n. And now we say, look, this is pretty straightforward. You see, there's a bunch of 100s. You can cancel all but one of them. That'll be left upstairs, 100. And this n plus 1 factorial is the same as n plus 1 times n factorial. Those cancel. So it's like 100 divided by n plus 1. And now, as you let n go to infinity, that goes to 0, which is definitely less than 1, which means, woohoo, converges. And you said, look, it converges without that plus minus, which means not only does it converge, but it's very strong convergence. This is an absolute convergence. Now, 2 down, 1 to go. If you believe what I said, that, hey, one of these is going to diverge, then you can say, okay, process of elimination, this one's got to diverge. But let's suppose you didn't believe me, because look at it. No, seriously, look at it. What do you see? If you stare at it, you're like, wait a second, hold on a second. This is alternating. There's a minus 1 to the n, and then because you have this part, okay, yeah, it does whatever, cosine whatever. But see, when I divide by n, this is getting close to 1. So this inside part is going to 1, which means that this whole part goes to 0, and then times, you have this alternating thing going to 0. Shouldn't that converge? Where? What? This is confusing. What's going on here? Okay. So here's the question. Is this actually alternating? What do you think? It kind of feels like it should be, right? When we stare at it. Because you see that minus 1 to the n. But feeling like it should be is not the same thing as it does. Okay, so let's be careful here. And in particular, let's look at this part. This cosine pi n. Now, what is cosine pi n? You might say, oh, well, cosine is just bounded, doesn't do much. But in particular, let's think about what it does. When n equals 1, you get cosine of pi. So if you think of your unit circle, so here's 0, pi. So that would be, the x-coordinate would be negative 1, 2 pi, back to 1, 3 pi, back to minus 1, 1, minus 1, 1, minus 1. So what happens is cosine pi n is actually secret code for minus 1 to the n. All right, well, what does that signify? Well, it really says, hey, there's something that looks like it's alternating there, but there's also this other piece that alternates there. Do they actually cancel each other out? Now, one other thing to know. And what is that? So we'll make a note over here. If you look at the function log of 1 plus x near x equals 0, well, what it does is there's an asymptote, and it comes off the asymptote and passes through at 0. The tangent line is very easy to compute, and it's the line y equals x. So the punchline is that log of 1 plus x is very close to just x, as long as we're near 0. So what does that say? Well, it tells us, look, this minus 1 to the n log 1 plus cosine pi n over n is approximately minus 1 to the n times this cosine of pi n over n, which is approximately minus 1 to the n minus 1 to the n over n, because we said cosine pi n is like minus 1 to the n. Or the two parts actually undo each other. It's behaving like 1 over n. So, in particular, what we can do is say, aha, by limit comparison test, with the sum from n, with the sum of n equals 2 to infinity of 1 over n, that's what we're comparing it with, this sum diverges. And there we go. So it's a diverging sum. Now you might say, well, wait, if we remove this part, will it converge? And the answer is yes, it would. But we don't have something called conditional divergence. When we talk about diverging, it says the sum as given. And so the sum as given, the terms are behaving like 1 over n for large n. That's what this computation shows. And therefore, since the sum of 1 over n diverges, this also diverges. So this is one of our, be careful, because we know what people look for. People say minus 1 to the n, their brain just says, okay, alternating, and then shuts down. We don't want you to do that. We want you to say, okay, that part is alternating, let me just make sure nothing else is going on. And here, there was something suspicious. When you see things like cosine pi n, you should be like, that's suspicious. That looks an awful lot like minus 1 to the n. I'm going to pay attention to that because I don't want to get tricked. I want to make sure I get this one right. Okay, well, fun. Good problems, good problems. On to our next problem. So, determine if the sum from 1 to infinity of cosine pi over 2 to the n squared of n diverges, converges conditionally, or converges absolutely. All right, so, now we see a 1 over root n. We're thinking, oh, it looks like a p-series, but it's a diverging p-series. If we didn't have that cosine upstairs, this would diverge. So the question is, what does that upstairs do? So we should think about what's happening with cosine pi over 2 to the n. So if we think of our unit circle, if we start here at 0, pi over 2 would be straight up pi, 3 pi over 2, 2 pi, right? So we're just going to doom, 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 doom. Okay? So cosine pi over 2 is 0, because that's our x coordinate. Cosine pi, minus 1. Cosine 3 pi over 2, 0. Cosine 2 pi, plus 1. So we're going to go as a pattern 0, minus 1, 0, plus 1. And then we're just going to repeat do, 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 so forth and so on. So let's see what's happening here. So we can say the sum from 1 to infinity of cosine pi over 2 times n over root n. Okay, so starting at 1, that would be a minus 1 over square root 1. Oh, sorry, starting at 1 would be 0, right? Because cosine pi halves is 0. Aha! I can still think. Okay, n equals 2. Cosine pi, that's a minus 1. So minus 1 over root 2. Then 3 pi over 2 is another 0. Plus 0 over square root of 3. 4 pi over 2, that's 2 pi. That's a plus 1. So plus 1 over square root of 4. And we're going to keep the pattern going. So 0 over square root of 5. Then it's going to be minus 1 over square root of 6. Plus 0 over square root of 5. Minus 1 over square root of 7. And, square root of... Oh my goodness. I'm going too quick here. I should slow down. Plus 0 over square root of 9. Plus 1 over square root of 10. And so forth. Now, is this as is? Is this of the right form for alternating series? And why not yet? It's not yet. Now the problem is the zeros. Because alternating series say, look, I need to alternate the sign and go to 0. But the problem is we have all these extra zeros in, which are like sort of throwing us off. But what do we know about 0? So look, zeros don't really do anything. So we say, okay, hey, this is the same as, if we ignore the zeros, minus 1 over square root of 2, plus 1 over square root of 4, minus 1 over square root of 6, plus, oh, whoops, there should have been a plus here. There should be a minus there. All right. Yeah, you should learn, don't go too fast. You get into trouble. Minus 1 over square root of 10, and so forth and so on. And so now we're like, great. Well, what happens here? Well, now we are alternating sign. So it's like, okay, the original sum, not quite, but okay, when we think about what happens when we add things up, if we ignore the zeros, this would be our sum. Well, we can say, hey, that we can write as a sum. Let's start from 1 to infinity. The plus minus says we're going to go minus 1 to the power. And now we say, okay, look, it's a square root of something. And we're going to have our square root being 2, 4, 6, 8, 10. These are twice the numbers, right? Twice 1, twice 2, twice 3, twice 4, twice 5. So 2k. And so we have our great aha. Yes, this is a sequence which is alternating and going to 0 in a nice way. And so we say by alternating series test, this converges. Now, that's not enough to come to the conclusion that we need, because we need to say, does it converge, diverge, or absolutely converge, right? Converge conditionally, converge absolutely, diverge. So right now we know it's some kind of convergence. So alternating series test gives that it's a converging series. And then we say, okay, but what happens if we drop the minus 1 to the k? 1 over square root of 2k, well, this will diverge. And how do we know that? Well, the 2 doesn't make any difference. You can even pull the 2 out. And what do you see? It's a p-series. It's essentially a p-series. So we know that the sum converges, but if we drop the plus minus, it diverges, and therefore we put these together. We say, okay, this is conditional. Conditional convergence. And we're done. We found the answer. All right. Well, this just says, okay, be careful and watch what happens. Well, good. I think we have time for one more problem. One good one to finish us up. So, here we go. Determine if the following are absolutely convergent, conditionally convergent, or divergent. Okay. Now, let's take a look. Now, one of the things that we should be able to do is sort of start to eyeball and say, we can get a fairly good idea of what's happening by just taking a look and saying, what's the behavior? So for the first sum, we say, well, that's geometric. And we know geometric, you converge as long as what you're multiplying by at every stage is small. And here, it's definitely smaller than 1 because it's like minus a half. And we say, well, look, what if we got rid of the minus sign? All right, great, a half still converges. So we say, look, we're going to jump straight to saying, let's do the sum without the minus sign. So since if we drop the minus sign, we would have 1/2 to the n converges, and we know it converges because it's geometric, and 1/2 is smaller than 1. we can say the sum is absolutely convergent. All right, that was pretty quick. No problems, except for spelling convergent. Everything else was pretty good. All right, now let's look at the next one. The sum of -1 to the n over square root of n. And we're like, ooh, this looks like a p-series. Here, square root of n is n to the half. We say, well, look, without the alternating sign, that's bad. But with the alternating sign, you're fine. So we say, okay, we can say the sum is converging because we have the alternating series test, right? Because we see that plus, minus, and then there's that square root of n. But if we look at this sum, n equals 1 to infinity of just 1 over square root of n, this diverges, and because y, p series, and where p is a half, which is less than or equal to 1. So the conclusion is that the sum is conditionally convergent. It's going to be the case that, all right, it converges, but you need that minus sign showing up where you alternate. Okay, 2 down, 1 to go. How about this last one? The sum sine of n over n log n squared. Now, you might be tempted to say, hey, sine of n, won't that alternate sign? Kind of, but here's the problem. You're looking at sine of n, not like sine of like pi n or sine of pi over 2n. And what happens is you're looking at sine at spacing 1 apart. But how does sine repeat? It repeats every 2 pi. Well, 2 pi and 1 are not very compatible. So it's kind of a sporadic thing. So you'll get some which are positive, some which are negative. You'll get numbers close to 1, you'll get numbers close to 0, and it can be like maybe you get 2 positives in a row or 2 negatives in a row. So it's not going to be an alternating. So that sine of n is very like, ugh. And so it makes us very nervous. So be careful. This by itself is not enough to be alternating. And indeed, it really throws a wrench into things. So we say, okay, let's not try to do anything with alternating series. Let's just say, maybe we'll be in luck and it'll be absolutely convergent and life is good. One of the things that we can do really quickly is just sort of glance at it and say, is this going to 0 or not? Because we have this test, right, that says, oh, if the terms don't go to 0, then we're done, the nth term test, or the basic divergence test. But here we can say, okay, the denominator does get big. Okay, so we can't rule out that this diverges simply because the terms don't go to 0. Or rather, we can rule that out. Excuse me. So now we're kind of like, ugh. So here's sort of our idea. Let's do what we did here and say, well, let's try to say, what happens if we take the absolute value? Now, what can we say? Well, the absolute value of sine of n over n log n squared. The nice thing about sine, even though it's true that we're sampling at really bad points, we know that sine, it oscillates between positive 1 and negative 1. So this numerator is bounded by 1. So this is below 1 over n log n squared. And certainly because we're taking the absolute value, it's above 0. If this sum converges, then that sum converges. If that sum converges, then that sum converges absolutely. Because what does it mean to be absolutely convergent? Absolutely convergent means when I take the absolute value of every term, it's still converging. So that's where the absolute comes in, absolute value of every term. So can we say something about this sum? All right, well, what test works well for sums of the form 1 over n log n squared? There's one test which is almost tailor-made for this one. And here we'll do the integral test. The integral test is its time to shine. Because if you think about what's happening here, when you look at this as a function, x log x squared dx, you're like, ooh, look, check it out. Check it out. See, if you set this part to be u, so you said u equals log x, then your du is 1 over x dx. And you're like, wow, perfect. Like we said, it's almost tailor-made for a series like this. So we say, okay, this will become integral log 2 to infinity, because as x goes to infinity, u goes to infinity, because log x gets big. Then it'll become 1 over u squared du. Well, that's minus 1 over u. Evaluate that from log 2 to infinity. And of course, when we say, plug in or evaluate at an infinity, we say, well, what's happening as we go to infinity? It goes to 0. So we end up with 0 minus 1 over log 2. We don't really care so much that the answer is 1 over log 2. I mean, it's nice to know. What we care about is that we got an answer. So we can say, okay, so integral test, we have that this sum converges. So now we say, okay, since this sum converges, we say, aha, this sum is going to be absolutely convergent. So there we go. And we're done. All right. Well, that's a little bit more subtle than perhaps some of the other ones, because you have to think about, okay, what's happening with sine of n? And there are things that we aren't ready to answer yet. Not that it can't be answered, just that we don't have the tools. So if we ask, how about the sum of sine of n over n? Does it converge or diverge? Well, we don't know. We don't have the tools. But it's not to say the tools don't exist, just that we don't have them. Not yet. But perhaps someday, if we go far enough in math, we'll pick them up, because they do exist. They are out there. All right, wow. A fun set of problems. And we're getting to the point where we essentially have collected together a nice set of tests so that we can start to say, hey, we know when this converges and we know when this doesn't converge. So now we can really say with some confidence, we know which series are interesting and which ones are hopeless. Well, that means some fun stuff ahead. So keep coming. Good times ahead. And so I hope to see you again. Bye.